Park at Stanford Research Institute, where they shared ideas on UFOs and consciousness. Jack thinks UFOs are human time machines, visiting the past to secure and protect their future. During his visit to us in France, Jacques Sarfati explained how UFOs use physics to manipulate gravity, space, and time.
So the math of Plato's objective reality invariance is the tensor calculus, which Einstein had to struggle. It took him 10 years with the help of his mathematical friend Marcel Grossman. He had to learn the tensor calculus in order to get that equation, G equals KT. And once you understand really what that gravity field equation, capital G is capital K, capital T, manipulate K, control the universe. When you understand that, then you become a Time Lord. Okay? In a real sense, that you can travel in time, you can manipulate gravity, and also you can shoot down any. I mean, you have an F-18 coming at. If I have a warp drive vehicle where I can control the gravitational field, and if you try to shoot a nuclear missile at me, I can make that missile bounce back in kind of a force shield, kind of a sort of an anti-gravity force shield. I can jam your electronics. I can make you crash. If you have a nuclear weapon in a silo, I can deactivate your nuclear weapon, which is what they're doing. So that's what we're talking about here. Yeah, let's be very clear. That's what we're talking. So when Travis Taylor says G equals KT, manipulate K, and control the universe, he's talking about the most advanced weapon system there is, which we actually see. That's what the non-human intelligence are. And they're showing, and they're neutralizing our nuclear weapons. Hopefully they've neutralized all our nuclear weapons so we can't kill ourselves in nuclear war. But of course I could be wrong. You know, that's the best case scenario. So this is the big picture of what's going on here. This is more than speculation. This is survival.
Professor Dave here. Let's learn the laws of thermodynamics.
He knows a lot about the science stuff. Professor Dave explains.
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing. Within a system, there is also a tendency to go towards higher entropy. The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random. That's far less information that needs encoding. which is a way of rationalizing why increasing the entropy of a system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more disordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around, entropy. The third law states that a perfectly crystalline solid at absolute zero has an entropy of zero, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system. It is enthalpy, the thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own. Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If positive, it is non-spontaneous. So we can use this equation to see how a spontaneous process can be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, and delta S is positive, which means an increase in entropy, which is also favorable, a negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T, so entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand, because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap. You need soap to wash non-polar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long non-polar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the non-polar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water-soluble due to the polar heads facing out. That's how soap works, and that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy-storing processes. In this way, systems can defy entropy on the small scale, but the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Let's talk about Boltzmann's constant. It's named after, first of all, this guy, Ludwig Boltzmann, who was a genius. He lived in the late 1800s and early 1900s. And he was the father of modern atomic theory, one of the big proponents, early proponents, that the world is made out of atoms and molecules. This sounds obvious to us now, but 120 years ago, it was definitely not obvious. And some of the smartest people of his day vehemently disagreed with Boltzmann, and Boltzmann had to defend these ideas over and over. And what I mean by atomic theory is this. If you had a container of, say, anything, could be a cube of metal, let's just say it's a gas. Let's say it's a container and it's full of air. Well, it feels like the air's continuous in here. Or like the gold. If this was a cube of gold, the gold is continuous. But we know now, and Boltzmann knew, that it's really made out of atoms and molecules. That wasn't obvious 120 years ago because you can't see the atoms and molecules. If this was a container of steam, let's say, and you stuck your hand in here. So I took my hand, I put my hand in this container of steam. I'd notice it. I'd know something was going on. My hand would start to feel hot. There's energy being transferred here, but it wasn't obvious what exactly is the mechanism. Is this a new kind of energy? Is this one of our old kind of energies just in disguise? Boltzmann's big claim and groundbreaking idea was that this gas, if it's steam, let's say, is really made out of atoms and molecules. These gas molecules are running around in here. There's just little particles in here. And what you're actually feeling are these particles striking your hand. So your hand's just getting bombarded by these particles, but they're so small and there's so many of them, you can't really tell that there's particles. It just looks completely continuous. So for Boltzmann, this heat energy isn't really a new kind of energy at all. All this heat energy that you're feeling is just kinetic energy. And if it's steam, it's just the kinetic energy of the H2O molecules flying around in here at some rapid speed. And the faster they go, the greater the impact with your hand, which is going to transfer more energy. So the faster they go, the hotter it feels in here. So for Boltzmann, to say that something has a high temperature, if you said that the temperature is large, if it's hot outside, that's kind of redundant. We already had a word for that. We could just say if it's a high temperature, what we really mean is that the average kinetic energy of the gas molecules outside is large. So if a gas has a high temperature, the average kinetic energy of those molecules is large. That's why it hurts when they impact on your skin, because they're transferring kinetic energy to the molecules in your hand. And when your hand absorbs too much energy, these molecules move around, your skin starts to get damaged, you can get burned. So this is often referred to as the kinetic molecular explanation of temperature. And the details of this theory were one of Ludwig Boltzmann's biggest contributions to science. But what does any of this have to do with Boltzmann's constant? Well, let's get rid of all of this. You've probably heard of the ideal gas law, PV equals nRT. So remember, T is the temperature measured in Kelvin. P is the pressure, and I'm going to measure this pressure, and I'm going to choose to measure it in pascals. V is the volume. I'm going to choose to measure it in meters cubed. And N, little n, remember little n is the number of moles of the gas. And if you forgot what moles are, N, the number of moles, is defined to be capital N, the number of molecules in the gas, the total number of molecules in the gas divided by a constant, and that constant's called Avogadro's number. And if you forgot Avogadro's number is 6.02 times 10 to the 23rd, and there's that many molecules per mole. So in every mole of a gas, what we mean by 1 mole of a gas is 6.02 times 10 to the 23rd molecules. And if you choose these units, this R, this gas constant, R is called the gas constant, and it has a value, R has a value of 8.31 joules per mole Kelvin. That's the gas constant R with these units. But these are pretty macroscopic quantities, pressure and volume and temperature and moles. Even moles, talking about 1 or 2 moles, is talking about a huge number of molecules. You're kind of glossing over some of the microscopic details. So an alternate way to write the ideal gas law is P times V equals capital N. So forget moles. Let's say we want to talk about how many molecules there are. Instead of writing little n, let's write big N, number of molecules. We'd need a different constant because we're going to multiply by the same T. So again, this T is still temperature in Kelvin. P is still the pressure in pascals. V is the volume, again, in meters cubed. N, instead of being the number of moles, is now the number of molecules. And that means we need a new constant here. We need a different constant. That constant's got to be really, really small. The rest of this stuff's the same. P times V and T are all the same. And all I did is I swapped out little n, number of moles, for big N, number of molecules. So this is going to be a huge number we're plugging in this spot now. Instead of plugging in, like, say, 2, if I were to plug in 2 moles right here, the number 2, down here I'd plug in 2 times this. So I'd plug in 12.04 times 10 to the 23rd. Since this is a huge number, I need a constant that's really small because it's got to balance out. We know that n times r has got to be the same as capital N times this constant, because the rest of this is the same. This left-hand side's the same and the t's the same. So if this is all consistent, then n times r has got to be equal to n times this new constant, and that new constant is Boltzmann's constant. It's a lowercase k with a b on it to denote Boltzmann's constant. So what's the value of Boltzmann's constant? We can find it pretty easily. We know that little n times r has got to equal big N times Boltzmann's constant. So if we just solve this for Boltzmann's constant, we're going to get little n over big N times r. But what's little n over big N? Just look up here. We can figure it out. Little n over big N, if I solve this for little n over big N, what I'm going to get is, if I divide both sides by big N, I get 1 over Avogadro's number. Little n over big N right here is Avogadro's number, or 1 over Avogadro's number. So I get that 1 over Avogadro's number times the gas constant, this 8.31, is Boltzmann's constant. And if you multiply that out, the gas constant, which is 8.31 joules per mole Kelvin, and divide by Avogadro's number, which is 6.02, times 10 to the 23rd molecules per mole, you'll get Boltzmann's constant, which equals 1.38 times 10 to the negative 23rd joules per Kelvin. This is Boltzmann's constant. This number right here is Boltzmann's constant. Why do we care about Boltzmann's constant? Well, it allows us to write a more microscopically oriented version of the ideal gas law that focuses on number of molecules instead of number of moles. And this number pops up all over statistical and thermal mechanics. It's one of the most important constants in all of thermal physics, in fact. It was so important that on Boltzmann's own gravestone, if you go to Boltzmann's grave, there's a bust and a gravestone. It doesn't actually look like a cross, but there's a grave there with a big inscription, and there's an inscription. The big inscription is an equation, S equals Boltzmann's constant times log W. This was possibly his most important contribution, and it says that the entropy of a system is equal to, this K is Boltzmann's constant, we just talked about that. Log, it says log, but nowadays we use ln because really they meant the natural logarithm here, and nowadays it's conventional that log is log base 10, but this equation is really referring to the natural log. And W is kind of mysterious like entropy is. W is the number of microstates. So if you had a macroscopic system and you wanted to know microscopically what are all the ways I can arrange my particles with given speeds and distributions and positions such that it looks identical, the macroscopic state for someone standing out here, they would look at this thing and they'd be like, that's the exact same state. But the particles are doing something different in here. It's just on a macroscopic level, identical. How many ways are there to do that and still make the macroscopic view identical for this person out here? That's what this is measuring, the number of microstates. And if you take Boltzmann's constant times the natural log of that number, it gives you an idea of the entropy. Entropy is very mysterious and interesting. It has to do with the disorder or available energy in a system. I don't have enough time to describe it right now, but if you have time, you should look into this. This is mysterious and confusing and wonderful at the same time.
So all bodies and systems possess a property called temperature. And most commonly, temperature is used to refer to how hot or cold something is, but the real sciencey definition of temperature is that it's a measure of the average kinetic energy of the particles in a system. So I've got a system and I'm filling it with little individual particles, and if we think about this microscopically, each little particle in the system is moving in some way, whether in rotation or in a straight line or curving by kind of a combination of these means. All of these little particles are moving, and the energy of motion is called the kinetic energy. So all of these moving particles have kinetic energy. And so the faster those little particles are moving, the greater their kinetic energy. And if each of those little particles in the system has greater kinetic energy, that means the system as a whole has a larger amount of total energy, and we would say that it has a greater temperature, because again, temperature is a measure of the average kinetic energy of those particles. And because knowing the amount of energy in a system can be really useful in chemistry and in physics, we've developed temperature scales to help us quantify or measure the amount of this value of energy. So the three scales most widely used are the Kelvin scale, the Celsius scale, and the Fahrenheit scale. So Fahrenheit scale. And for all of these scales, I'm going to draw a little thermometer. So one for Kelvin, and then we have a thermometer for Celsius, and then another thermometer for the Fahrenheit scale. And the two scales used most in the physical sciences are probably the Celsius scale and the Kelvin scale. So as a point of comparison here on these thermometers, the freezing point of water occurs at 0 degrees Celsius. So we have 0 degrees Celsius, that's where water freezes. And then the boiling point of water occurs at 100 degrees Celsius. So the boiling point of water occurs at 100 degrees Celsius. That's where water turns into steam. And I'm going to write H2O here real quick just so we don't get confused that we're talking about the freezing and boiling point of water. Now when we use the Kelvin scale, we find that water's freezing point is 273.15 Kelvin. And then we find that water boils at 373.15 Kelvin. So they differ fundamentally in the 0 point. The Celsius and Kelvin scales differ in the 0 points that they use, but between water's freezing point and water's boiling point, we have a span of 100 temperature units for both scales. So although they differ in the 0 points that they use the same size unit or the same magnitude of unit to measure the temperature. So converting then between the two scales only really requires that we make an adjustment for the two different 0 points. And this is what I mean. If we want to know the temperature in Kelvin, all we need to do is take the temperature in Celsius and add 273.15 degree units to it. So if we want to know the temperature in Kelvin for the freezing point of water, we take the temperature in Celsius, which would be 0, and we add 273.15 units to it, and that would give us 273.15 Kelvin. Now if we want to flip that, and if we want to find the temperature in Celsius from Kelvin, all we have to do is take the Kelvin figure and subtract 273.15 to it, or subtract 273.15 from it, excuse me. And so we would see that 373.15 Kelvin minus 273.15 would give us 100 degrees Celsius. So just as another example, let's convert 300 Kelvin to Celsius. And to start, since we're looking for Celsius, we'll take that Kelvin value and we'll subtract 273.15 from it. And that's going to give us 26.85 degrees Celsius. So 26.85 degrees Celsius is the same thing as 300 Kelvin. And I just want to point out really quickly that I'm only using the degree symbol here for Celsius. And I'm doing that intentionally. We don't need this symbol with Kelvin scale because instead of calling the temperature units degrees, we just call them Kelvin. So the only thing we need is an uppercase K. Now, converting between the Celsius and Fahrenheit scales is a little bit more complicated. You see, in Fahrenheit, water freezes at 32 degrees Fahrenheit. So 32 degrees Fahrenheit, and water boils at 212 degrees Fahrenheit. So 212. And this gives us a span between the freezing point and the boiling point of water of 180 degree units. So we're going to need to consider two different adjustments here. One for degree size, because the units have a different magnitude. The same value or the same span of temperature is 100 units in Celsius and 180 units in Fahrenheit. And we're also going to need to account for the two different 0 points, 0 degrees Celsius for freezing and 32 degrees Fahrenheit for the freezing point of water. So first we can say that 180 degrees Fahrenheit is equal to 100 degrees Celsius. And again, we can say this because both of these magnitudes refer to the same change in total energy. And so if we write this as a ratio, we have 180 over 100, which just reduces down to 9 over 5. So the ratio of Fahrenheit to Celsius is 9 to 5. Now we need to think about the two different 0 points. And because 32 degrees Fahrenheit is equal to 0 degrees Celsius, we can find the Celsius temperature if we take the temperature in Fahrenheit and we subtract 32 degrees from it. And this makes sense because 32 degrees Fahrenheit minus 32 degrees Fahrenheit would give us 0 degrees Celsius. And now we just need to apply the unit ratio. So just like any dimensional analysis problem, we need to cancel out the degrees Fahrenheit. So if we put the degrees Fahrenheit on the bottom here, so 9 degrees Fahrenheit, we can cancel out the Fahrenheit, leaving us with just degrees Celsius. So to find the temperature in Celsius, we take the temperature in Fahrenheit, subtract 32 from it, and multiply it by a ratio of 5 to 9. And then we can also manipulate this formula if we want to start with Celsius. So all we have to do is solve for the temperature in Fahrenheit. And so to start, we would divide both sides by 5 over 9, or that's the same thing as multiplying by the reciprocal. So, and then to finish it off, we would just add 32. So plus 32 is equal to the temperature in Fahrenheit. So now, if we want to start with temperature in Celsius, we can move to temperature in Fahrenheit, or we could start with temperature in Fahrenheit and move to temperature in Celsius. And so to practice this, let's go from Celsius to Fahrenheit, and it turns out that these temperature scales actually cross paths at a temperature, which is kind of a fun fact. So if we plug in -40, let's go from -40 degrees Celsius to Fahrenheit, we'll find that TF is equal to -40 times 9/5 plus 32. And so we can reduce this term here, so 5 and -8 or 5 and -40 reduces to -8. So -8 times 9 plus 32. That's -72 plus 32. So the temperature in Fahrenheit would equal -40 as well. So -40 degrees Celsius is the same thing as saying -40 degrees Fahrenheit. That's kind of just a fun fact. And another observation from this little factoid is that Celsius and Fahrenheit scales can both have negative or positive values. We see that both can be -40, so these can both have negative values. And that's actually a point where they differ from the Kelvin scale. The Kelvin scale can only have a positive value. And it turns out that the absolute coldest temperature is 0 Kelvin. So 0 Kelvin is absolute 0. And the reason we can't get any colder is that at this point no particles would have any kinetic energy. And so that means no motion at all. We said that temperature is a measure of the kinetic energy, and the coldest that you can get is no kinetic energy whatsoever. And it turns out that the laws of physics, specifically the uncertainty principle, just don't allow for this. So we can get close, like within a billionth of a Kelvin, but we can't get all the way there. And because Kelvin scale always has a positive value, it becomes a little handier in various formulas. And so it's used as the standard, the SI unit for temperature. So I'll show you in future videos why absolute zero happens at negative 273.15 degrees Celsius. But I'm starting to run out of time in this one, so I'm going to have to save it for later, and I'll talk about that with Charles' law in the future.